Okay, let's get started then. Has anyone seen this image before?
Yeah.
What's that?
Earth.
That's correct.
Whoa.
All right, what is this?
What are you doing here?
I think it is.
Look at that.
It's in the other room. No. Yeah, it's on the chair. Okay. So what are you looking at? I'm not to the clouds, yes, that is certainly there, but that's not why I'm showing you this today.
The clouds.
Not just the clouds, look closer. Yeah, the shadow. So what you're looking at right now is the rotation of the Earth around the sun. This is from a geostationary satellite called the GOES-R satellite. And what you're seeing is the orientation relative to the sun. So the shadow moves back to here and then back to here. What is this season for the Northern Hemisphere?
Winter.
For the Northern Hemisphere?
Oh, summer.
Too many beers at lunch. Okay, what is this one? Winter, what is this one?
Spring or fall.
Very good. So there's an ambiguity there. And in fact, that is the ambiguity that you find yourself in right now. It's what we call the vernal equinox, where days are now equally long and short. Yeah, thank you. Okay, everyone happy?
Yes.
Cody's asleep, that's okay.
All right.
What's that? We have half of them off actually. That's half? Front door? Can you just get rid of that one? What is that one? Yes, let's go. All right, what's that? Correct. And the joke is? You like it? What's you saying that I have really good jokes? They
Yes.
always hit exactly the same.
Exactly.
What's older, trees or Saturn's rings?
Trees.
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 What's older, sharks or Saturn's rings?
Two.
Wait, really? Yes. How old are Saturn's rings?
Too young.
2? Not a number.
Too young.
Too young? Not a number.
Under
2 million years? That would be a number. I like that as a number. That's it's about or a factor 50 off. So Saturn's rings are thought to be maybe as young as 100 million years old. And they're formed because this used to be a moon, and Saturn was like, not anymore. And destroyed the moon. Yes.
Trees are older than that.
Yes. Sharks are older than that. Sharks are 350 million years old. The sharks basically figured out how to murder, and then they just did it forever. Yeah. I'm not saying a single shark. I'm talking about the species, right? Okay.
I mean, humans can make food, but we're not living long.
That's a longer story. Okay. So let's have a look at another. So this is a real image, by the way, in case folks are forgetting that. There are some stars in the background here. The sun is behind them. This is a view from when the sun is behind you and you're looking at it. And overlaid on it, of course, is the fact that there are aurora here. This is the blue coloring. So this is the Hubble Space Telescope. You have 2 images, one in the visible and one in the ultraviolet. And you see the aurora is where the magnetic field lines are connecting the solar wind into the planet, smashing into it and making it light up. Okay, if you think about how big these are, right? Look at how big the planet is, look at how big the rings are. How thick are they? 20 Earths tall? Yeah. Okay. So if we go back to this photo here, let's say an Earth is like this, right? You think these are comparable size to that? 20 Earths tall? Let me ask you a different question. Let's make it the size of 10 football fields. Okay,
Saturn is a.
let's say the rings are 10 football fields wide. How thick is it in like those same scales?
That's 10 football.
Yes. Okay,
One football.
one football field? Raise your hand for one football field. Raise your hand for smaller than one football field. Raise your hand for bigger than one football field. Okay. What's small in a football field?
3 feet.
3 feet. Raise your hand for 3 feet.
Like each ring or like.
No, like
all of it
so
together.
if it's wide like this, 10 football fields, how tall is it?
Oh.
3 feet? Tennis ball? Raise your hand for 3 feet. Raise your hand for tennis ball. Raise your hand for in between. Raise your hand for piece of paper.
That's wild.
Piece of paper. Piece of paper. It's incredibly thin. Incredibly thin. That's an artist's conception. That's not a real picture. The thickness here, roughly, is paper weight in that same scale. Okay?
So what?
The ratio here between the width and the height is like a piece of paper to 10 football fields. It's great. Okay. Look at that on the edge. Oh. That's the scale. It's slightly tilted so that you can see it at all. But there are some fun things to see here. Okay. So Saturn is off to the left. Saturn is not in this image. Those are its rings. And you have fun things called moonlets, little baby moonos. Okay. They don't always look circular. They don't look circular because they're not large enough for gravity to squish them. So if you look very closely, that kind of looks oblong, right? Like a football, right? So that's a moonlet. This one here is, I think that's Enceladus. And then the one behind it is Titan. Titan is the largest moon. And you can see it's big. Okay. Make sense? Okay. Moons shepherd the rings. You see this? As they move through, they create spiral density waves in the rings themselves. And they like bunch the material up and they create shadows. See this? In front and before. Okay. Saturn also has an atmosphere. It's pretty badass. Not as badass as Jupiter's. Jupiter's is way cooler. But you can see here it has massive storms. We said at the very beginning, or at the end of last class maybe, we talked about the south and north pole of Jupiter. And here you can see this is the north pole of Saturn, and it has hexagonal symmetry. Remember the north pole of Jupiter had fourfold symmetry, like a cross. And here the storms work out to make this cool hexagon. Aliens, right? Of course, always. Okay. This is a video. Hopefully it runs. Go! Movie time!
Yeah.
You hit the other one, Caesar.
It's springtime on Saturn, and the hexagon is out. A perfect six-sided hurricane, 60 miles deep, that could swallow 4 Earths. It's ringed by winds of ammonia and hydrogen blowing 220 miles an hour. The storm was seen by the twin Voyager spacecraft when they passed by in the early 80s.
That's how pictures used to look.
That was the last time until recently that sunlight graced the North Pole of Saturn, which takes 30 of our years to make one circuit of the sun. Soon after the Voyagers departed, winter descended. Saturn's rings tipped away from us, plunging the North Pole into 15 years of darkness. Without sunlight, astronomers were limited to infrared images. They showed the hexagon was still there. But what is it? The hexagon is a narrow jet stream that circles the North Pole. Researchers think that friction with the slower clouds on either side of it creates eddies. mini storms that push the jet stream into a wave-like shape as it goes around. By spinning columns of water at different speeds, scientists have been able to reproduce the six-sided pattern in the lab. In January of 2009, the sun began its slow rise in Saturn's north. Summer was coming. The Cassini spacecraft was there to see it. In the coming months, Cassini will slip between Saturn and its rings to pass right over the storm for a closer look. But that's not all there is to see up north. Saturn has an aurora.
Okay. Pretty badass, right? So all we have to do, yeah.
How's it so like hexagonal?
Yeah. Good touch. What fluids you doing? I know. So if you're in fluids, you saw today that you can scale between something as large as Saturn and something as small as we could build in this room by playing with parameters of the fluid itself. And in particular, when you think about fluids on a very large scale, the viscosity of the fluid itself becomes a lot less important. The fluids you're talking about here are hydrogen and helium. Helium hates participating in any chemistry. So mostly you're talking about hydrogen. You're going to have storms, you're going to have all of this. But on large scales, the reason you have symmetry at all is because there's nothing underneath you that's breaking that symmetry. So you have some sort of storm that's developed from, say, winds that are going around in a circle, and there's no reason that one side should be better than the other. So what you end up seeing usually is one circular band, no variation. That's sort of what we think of it like the zero it. And then there are other harmonics on that. So the way I think about that is just like when you sing in a pitch, and then there's a half octave above it, you know, the full octave above it, everything else. Those are harmonics that exist within the fluid. This is probably exactly the right resonant forcing for exactly this fluid, such that it builds this weird shape. Weird, right? Does it matter to us? No, it's just fun. But I've had lights against it. Thank you. Okay. Wrong lights. Thank you. So, can you tell the difference between Uranus and Neptune?
Yeah.
Why?
Different shade of blue.
They're different blues. Anything else? One's smooth.
Just don't.
Like a smooth color.
Okay. If you touched it, what would happen?
I don't.
You go through freeze, actually, yeah, it's very cold. This is not a surface. This is what we call an ice giant, but it's not icy. This one here has a great blue spot. Do you see the blue spot? Okay. Yeah, this is a storm. But the colors that you're seeing here are methane based. Methane, ethane type clouds. The clouds that you saw before. These ones here are ammonia, water ice. Water ice tends to be very white. Hydrogen sulfide tends to be red. Whereas these ones here, which are methane, ethane based, very blue. Okay. And then you see some water ice clouds in here as well. These are Neptune. Neptune has rings. You can see them right here. There's Triton. We talked about it very briefly. I'd love to go into a lot of detail on all of the small planets. I'm like supposed to teach you about stars and stuff. So we'll do that next week. Okay. It's also got a ton of little moonies, like Naiad and Galata and Thalassa and Despina and Proteus and Larissa. What? Is that your?
Is that my name? Is that what you said? Is that my name?
Could be a middle name, you never know. All right. So those are Neptune's rings from JWST. And what you can see here is there's little moonlets forming in the rings. And JWST sees in the infrared. So really you're seeing kind of below the surface. And the places where we see these massive storms, you actually see what's called upwelling. which is material coming from the interior that's quite warm, just like your circulation and your miso soup might occur. And as it comes to the surface, it's quite warm, and then it cools by infrared cooling. Huh? Okay. You don't need to write any of this down, please don't. You can look it all up. But if you ask ChatGPT, it will get it wrong, and this is a really fun thing. Here you notice that Jupiter is about 5 times as far from the sun as we are. So we talked about AU, but let's just remember this as a measurement. Okay. Jupiter, 5.5, 5.25 AU. Saturn, about 10 AU. I'll accept that as the correct answer, 9.5, 10. Uranus, 19. I'll accept 20 as the correct answer. Neptune, 30. Okay. Look at the difference in the masses here. Jupiter holds about 318 Earth in mass. Saturn jumps down less than 100. Uranus and Neptune, 14 and 17. Is that weird to anyone?
Yeah.
Why is that weird? So similar, okay. Any other weirdness though?
Yeah, transfer not. There's no important.
No source of heat, okay. Yeah, this is like the total mass, right? So like Uranus has less mass than Neptune. People expect that? Do you have any like starting into this discussion, did you assume that Jupiter would be the biggest?
Yes.
Raise your hand if you assume Jupiter would be the biggest. Good. Did you assume Saturn would be second big? Yeah. Did you assume Uranus would be third big? No idea, right? Okay. Then it gets a little sketchy after that, right? Saturn is beautiful, it's got these big rings. You assume, okay, it's gotta be big, it's gotta be the second largest. Right? Here's the Earth radii. Interesting. Jupiter is 11 times the size of the Earth in width, for example. Saturn, pretty close to 10. Uranus, pretty close to 4. Neptune, pretty close to 4. What? Okay. This density here is really important. This is what we're going to compare gas giants to. So a number that is 1 in grams per cubic centimeter is the density of water. The density of water ice is about 0.9, which is why water ice floats to the top of liquid water. Less dense, right? Here, Jupiter is more or less dense than water. More dense than water. So if you put Jupiter into a pool, it would sink. That make sense? It's gotta be a big pool. Yeah. Saturn, more or less dense than water. More or less dense than water ice. Less. So in a pool, it will float. Uranus, more dense than water. Neptune, more dense water. Well, what the hell is going on here? The composition of these two is mostly hydrogen and helium. By the time you get to Uranus, I said that we have water, we have ammonia, and we have methane. And the same thing's true down here. So we call these the ice giants because they include water. And we call these the gas giants because they're just hydrogen and helium. Their clouds, the things we see at the top, are composed of water and ammonia and everything else. But their primary composition is hydrogen and helium. And in these cases, these are their primary compositions. Okay. So here's the densities shown next to each other. And then this really great animation that I made, floats in water. So why? Why is Jupiter denser than Saturn?
So big, presses it even further.
Okay, so big it compresses it even further.
Yes.
Yeah. Is there a surface on Jupiter? No. Okay, so it's just gas all the way down, right? So it looks like this. You have some like pillow of gas. It's a metaphorical pillow, it's not a real pillow. And as you place it on the top, it squishes all the pillows below it. So your princess with the P, you put the P down here, it gets crushed, right? Your head's up here. Everyone know this story, or is it just me? You don't know this story? Raise your hand if you know the story. All right, it's story time on Monday.
We watch movie?
It's a story. It's like a book that you read to children.
It's-
Yeah, it's a picture book. I'll stand at the front. We'll put blankets for everyone. Okay.
Left here on lab.
No. Okay. Okay. If you add mass to a planet, you compress the underlying gas layers, like pillars. So as I add this piece, it's gonna squish them off. So in fact, what ends up happening is if you add more mass, it doesn't necessarily always make the planet bigger. It just makes them more compressed. And it looks like this. So you keep adding mass to Saturn, okay? And the radius goes up. That's what we expect. But if you keep adding mass to Jupiter, the radius will go up, and eventually it'll hit a level here where it'll stop. And instead of getting bigger, it will get smaller with planets. Because you have a balance here between how much material is getting pulled in by gravity and how much material is being held up by the pressure inside. It's hot, and hot creates pressure, and then it comes back down. Makes sense? Okay. Questions? Okay. So we know now. Jupiter is denser than Saturn because its larger mass compresses its gas. What about Uranus and Neptune?
They're made of like heavier elements.
Yeah, which elements?
Nothing.
Methane, water. So if you're made of heavier stuff, you're gonna be denser, right? Bada bing, bada boom. So, you want to answer this question? Why are Uranus and Neptune denser than Saturn? The extra mass of Uranus and Neptune compresses their interior more than Saturn. They have a higher fraction of hydrogen compounds, rocks, and metals. Their cores are much larger than Saturn's. They have more hydrogen compounds than Saturn, or they have a greater ratio of helium to hydrogen than Saturn. We know when you're ready to vote. Let's vote on 3, 2, 1. Okay, this side all agrees, but this side does not agree so much. You want to turn those lights on so then we can have a little discussion. You guys can talk about whatever you want. We all agree.
Aliens?
Not here.
Always aliens. Yes. Yeah, let's talk about aliens.
Let me grab water. I'll be right back.
Okay. Wait on that.
I promise I have to read this. I know.
And Saturn.
You're not too tough.
Okay, everyone ready? Let's revote this up when you're ready to revote. Let's vote on 3, 2, 1. Okay, all right, so there's only two different votes here. Two different choices here.
I know.
Some people say the extra mass of Uranus and Neptune compresses their interior more than Saturn. Some other people say they have a higher fraction of hydrogen compounds, rocks, and metals. So let's go back 1 second here. Okay, here's the density of Saturn, 0.7. Uranus and Neptune are like 1 point something. Right? The extra mass of Uranus and Neptune compresses their interior more than Saturn. Who likes this answer? You want to defend this answer?
They have more mass or no?
Yeah, that's an interesting question. They have more mass.
I know.
Oh, almost like I just showed it. Which is the bigger one? Saturn or Uranus and Neptune?
Like,
Saturn. Oh, interesting. So this can't possibly be right, right?
Oh, no.
Oh, no. Good thing we're talking about aliens on this side. I was just hoping that you think about it. So let me ask you, so which of these other ones are still valid? One is not valid. Why do you like two? I don't know.
Well, because they just have more. Do they have rocks in the metal? I picked two, but I don't know if it has rocks and metals. Oh, I said the rock.
Yeah, rocks and metals. Yeah, we didn't really talk about that, did we? What did we talk about? What is
gases?
Gases. Okay. Did we talk about a ratio of hydrogen and helium? No. What do hydrogen compounds mean? H2 is hydrogen.
Things that bond with it.
Things that bond with hydrogen. What's an example of a hydrogen compound?
Water.
Water. What's a hydrogen compound that bonds with nitrogen? Ammonia. Didn't we just use that on Monday in order to make really cool comments that everyone loved? Okay. She's like, what? I don't think so. What is a hydrogen compound that works with carbon? Methane. CH4. Right? You have H2O. You have CH4. You have HCN. Right? That's hydrogen, carbon, and nitrogen. You have NH3. These are all hydrogen compounds. So even though 2 looks nice, we didn't talk about rocks at all. There's no discussion of rocks. In fact, rocks make a very negligible portion of their total mass. So this is kind of hard to get around. Because in our heads, we think, well, we have like a core and we have a surface and a thing, right? Jupiter says, okay? This is in the wrong order, but I'm going to go back to it. We're going to go forward and then we're going to go back. Here's what's inside. Okay? So you could live up here. There's 1 bar, 125 degrees Kelvin. That's a little cold. Okay? 2000, that's a little warm. You want to be right in here. Okay? So you want to live in the gaseous hydrogen part, right up here. You keep going, and hydrogen suddenly becomes a liquid. It's about 5,000 degrees. That's the surface of the sun. And the pressure is 2 million times the surface pressure on Earth. This is not something that we can conceptualize. Your brain is not evolved to understand what this feels like. Okay? And this is about the density of water. You've crushed hydrogen to the density of water. Yeah.
What does hydrogen actually look like?
What does it look like?
Like,
Yes and no. It's not going to be very meaningful for you to see, right? So the pressure here is 2 million bars. Hydrogen is going to look like hydrogen, but in a totally different phase, right? So hydrogen already looks like nothing to you. It has a few emission lines. That's it. H2, for example, has some emission lines that we see in the visible that make it look red, make it look a little like bluish. It's not gonna look like anything to you. Does that make sense? Yeah. And then as you keep going, you get something called metallic hydrogen. This is where hydrogen just like acts like a a metal like copper starts sharing its electrons.
Can we see that?
You wanna see it?
Seeing is not really like possible. Like seeing is something that we think about. So in order to see something, you need photons, right? So we can approximate what this looks like, but we do not make metallic hydrogen regularly in a lab. And if we do, we make it in a plasma sample. To get it to temperatures of 5,000 degrees, this is the surface of the sun, right? This is 1 bar. You go down here, look at this, it's 20,000 degrees. This is 4 times hotter than the surface of the sun, and that's just at the edge here. It's hot. Okay. There's the Earth for scale. Didn't even see that thing? So this whole thing fits inside of the, they don't know if there's a crust, but they think if there is a crust, a core, that the whole Earth would fit inside of the Jupiter's core. So kind of wild, right? Okay, so let's go back for a second. Let's talk about those top parts here. Jupiter and Saturn rotate about once every 10 hours. Pretty fast, considering how big these things were, right? You just saw how much bigger Jupiter is compared to us, about 10 times larger. Whereas Uranus and Neptune rotate every 15 hours. And what this does is, in the direction of the rotation, the edges here, they bulge out, just like you're a ballerina and your arms are going out along the rotation axis. Except there's compression in this direction due to gravity, and this is combating that same force in the rotational direction. So you get what's called an oblate spheroid. That's just a word you can say to your family this week.
Oblate.
Nope. Oblate
Oblate.
spheroid. So planets are oblate spheroids. Okay, cool.
Good.
Fun word of the day. That'll be on the homework later. Okay, so here's the cloud decks. They're pretty sick. All 4 of them look like this. This is the temperature, the function of altitude. And this is with respect to a reference altitude. And so what we see here is Jupiter is on the right-hand side, and it's the hotter one. Why is it hotter? These altitude levels are calibrated to pressure levels. Why is it so much hotter? So it goes Jupiter, Saturn, Uranus, Neptune.
Distance.
Distance from the sun is the important part here. So here at the top of the atmosphere, the fact that this is hot is because it's close to the sun. The fact that this is hot is because it's closer to the sun than these 2, but less than this one. Right? What causes the heating way up here? What's that?
X-rays.
X-rays and UV rays, just like on the Earth. This is warming the exosphere, the thermosphere, just like on the Earth. Okay? Is there ozone in this atmosphere? No, no bump. Right? So just gradual decrease all the way up, and then gets hot because of X-ray. You never thought, yeah.
I thought you said the sun doesn't affect the internal temperatures.
I never said that the sun makes this. I said this.
Oh.
In fact, you're right. Absolutely. So once you get below the cloud deck, where does the heat come from? And maybe the greenhouse gases, right? That would be a very good assumption. It's actually what ends up happening is if you only account for greenhouse, it does this.
Why is Uranus like not reached as high as like Neptune and Saturn?
This doesn't have as tall an atmosphere. Nothing wrong with it. Perfectly good. We've never been this far down. To go back to your point though, if you bring this temperature level down to low altitude, it's much cooler if you don't have any source of heating from below. But in fact, there's a massive source of heating from below. Jupiter shines brighter than the amount of light that it gets. That's the right face. You should look all as confused as Kobe, because that doesn't make any sense. Jupiter, I'll say this again, shines brighter in total illumination than the amount of sunlight that it gets. Yeah, very good. That's not right. But it must be something, right? So what does a star do? It makes light. How does it do that? Okay, so it doesn't do fusion. Otherwise, that would be sick, but not right. But it must be another source of energy, right? Like you're saying, they're not quite starry, but it's. It make light. Yes, it's true. But it makes infrared light. Still a form of light, but not very big light.
Aliens.
No. Not alien. What could it be? What are our sources of heat again? Never said friction. Energy. That's not a source of energy, that is energy. Differentiation.
Oh, no.
What?
Accretion
Accretion
and radioactive decay.
and a radioactive decay. Thank
For a
you.
while.
So these are our forms of heat. This is how I can get heat in a planetary body. Do I have radioactive decay here?
Maybe. Wait, where?
What?
On Jupiter.
Oh, no.
On Jupiter.
It's way there.
Why? Because it's mostly made of. Which ones? Are there unstable forms of hydrogen and helium?
Yeah.
No, what?
What is an unstable form of hydrogen? What is hydrogen gonna break into?
Hydrogen.
Yeah, if you have one thing, if you have hydrogen, it will not split into anything else. It literally, the proton is the most stable thing in the universe. As far as we know. Helium also doesn't like to participate in any chemistry at all. And it doesn't like to be reduced. How fortunate. How fortunate. So hydrogen and helium, they're not participating in any fun fusion. And they're definitely not radioactive. What's that?
They're boring.
They're boring. Okay. So there's no radioactivity, so that's weird. So we have two other forms of heating. What could it possibly be? Differentiation or
Accretion.
accretion? Which one?
Different.
Would it be differentiation?
Raise your hand for differentiation. Raise your hand for accretion. Don't raise your hand. I know. That's why I took them. Okay, so no one likes accretion. Why not?
When was the last time you saw a meteorite hit Jupiter?
Very good. When was the last time you saw a meteor or anything hit Jupiter? And in fact, it was in 1996 when the comet Shoemaker-Levy exploded on the surface of Jupiter.
That's what it's the left.
So that's very boring. Well, you get, I mean, this is something that I can go on and on about. You find a new thing, they name it after you.
Can I name it though, like if I find something?
They
Or
name
would it
it
be named?
after you.
It would be in the.
You can't name it like, lovepokemon.com. If your last name is McDonald, they'll name it after you. So if you find something, don't publish it. First change your name to whatever you want, and then publish, right? Big brain moves. So
What'd you do?
we're left with one more thing. And what is the last thing? It's not accretion, not radioactivity.
Differentiation.
Different. So what does that mean?
Isn't it like-
Differential.
One at a time, one at a time.
Density changes in the atmosphere.
Density changes in the atmosphere, okay. So how does that provide us with energy?
It moves.
Hopping, rise, and cool things fall.
Hot things rise and cool things fall. That's true right now in a mostly uniform atmosphere. But it doesn't quite give us differentiation. There's a corollary to it. There's a small caveat, an asterisk that I would put on your statement, which is
It moves the different layers and.
right. So that is how we give energy.
How we get there.
Heavy sink, like.
heavy sink, light rise, which is just a small, hold on, a small difference on hot rise, cold fall. Right? Hot rise, cold fall infers that the density is related to the temperature. Whereas in this particular circumstance, it's important that the more massive things are sinking. You have active differentiation in Jupiter right now. Is that crazy for anyone? No, no one cares.
What is it?
So in fact, the interior of Jupiter is quite warm. We saw that already, 20,000 degrees. And it's currently still separating into layers. Okay. There's different colors in the cloud decks. So at the very top, those yellow ones are ammonia. So you can think of that like the cleaning products that we played with. You have ammonium hydrosulfide. We did not play with that. That's very dangerous. So these are hydrosulfides. So what's the chemical element here? H.
Take this out.
Yeah. You can just say it loudly. I just wanted you to say it. And what's the ammonia? NH3. Good. So these are all very common. We've played with them all the time, right? Just kidding. I hate chemistry. Okay. And what about this one? This one's very rare. H2O. Yeah. Your question?
Why don't Neptunians blow up?
Blow up?
Yeah, because they're coming methane, right?
Ah, very good question. So methane is flammable.
There's no spark.
A spark. And also you need oxygen. So for example, combustion requires all of these different chemical elements in order to get energy out of it. So you're right, you look at methane and you're like, well, should I just like toss a grenade onto Uranus and like watch it go kablooey? But what's the primary component of Uranus? Hydrogen. Hydrogen. All four of these, the primary component is hydrogen. Now, hydrogen, what have I heard about that before? Stable? If I fill a room up with hydrogen and I chuck a grenade in, am I gonna have a good time? Wow, so what's the famous example? Which one?
Heisenberg.
No, not Heisenberg, that's Hindenburg, you bet. Hindenburg. I like Heisenberg too, but it's incorrect. So, humanity is the famous example of what happens when you rely on hydrogen fuels, because they're incredibly flammable. And yet we didn't immediately think about that when we thought about Jupiter, right? So if I toss a grenade onto Jupiter, it doesn't explode. Why is that? We already said it.
No,
No oxygen. Okay, no catalyst for the chemical reaction, right? Okay. So could we live here then instead? Right, so here's the temperature. I like to live at about 373 degrees Kelvin. It's about here. It's chill, right? Die. Die? Why die? All right. It's all right. You like it? Anyone want to live in the cloud decks of Jupiter?
Well.
If we're desperate.
No, like that's good.
Oh, I don't know what that is.
You know, often happen.
Folks, I don't know. I'm very old. Brain don't work good. Okay. So let's remember that this is still in the gaseous part of the top of the atmosphere. As we go down, the pressure probably gets too high. Right. The reason that it's getting warm is because the pressure's going up dramatically. So you notice here that the difference between this number and this one is a factor 10, and the difference between this one and this one is a factor 500,000. Okay. So this is not increasing like an ideal gas. In fact, it is not an ideal gas very soon. Okay. It acts like a metal at great depths. I said this already because electrons move freely, but it's not solid. So Zori decides that she wants to go visit. She gets into a nice little like capsule, and start sinking. And maybe it has a nice little porthole that we can look through with a little light inside, she's shining out. We start sinking, we're 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 sinking, all the way to the middle. Okay. It's very unclear whether there's a hard, solid core. A whole group of scientists are convinced that there's not. A whole group of scientists are convinced that there are. You could find out in the next 30 years. Yeah.
So when they mean by metallic hydrogen, so it's not like fully thought out that it's solid, but just acts like a solid, or what do they mean by metallic?
Solid and metal do not mean the same thing. Metals conduct electricity. Solids are things we can stand on. So in this particular circumstance, hydrogen acts like a metal because all of the protons and electrons are so close to one another that they're willing to share their electrons with nearby friends. So think about H2, for example. H2 is two hydrogens hanging out together, being besties, and sharing 2 electrons. And you say, oh, that's all well and good, but here's one H2 over here, and here's one H2 over here. And those 2 sets of electrons, they're not going to communicate any information. Whereas if I put them very close to one another, all of these hydrogen and protons and electrons, I make some change over here. I press on this part, and the electrons move out of the way. They move other electrons, they move other electrons, they move other electrons. That is the process of conducting electricity.
Like partially exposed. And that's not-
What is it?
Maybe. Yeah, no, it's fair. I'm trying to figure out where they hang. Yeah.
So this is metal. Okay, in this crystal structure, if I apply a voltage to this side and I get a response on this side, what happened? Did electrons flow from here through here to here? No, what happened? Right, so I pressed on this side, it pushed on the ones next to it, it pushed on the ones next to it, it pushed on the ones next to it, and it pushes like a wave. So all of the electrons actually stay with the atoms that they are hanging out with, right? But they press on their nearby neighbors, and those press on everyone else. So even though this is metallic, it's solid.
How can it not have core and still be good? Yeah, like,
Good question.
I don't, I don't understand how, why do people think that there's no core?
So it may have started with a core. It likely needed to have a core. But the question about whether it continues to have a core is very ambiguous.
It could just go away.
Yeah, think about this whole thing, right? It could have started very small. It could have started as a single object. You can have a number of ways to transport core outwards. You can lose it off the top. This is really high pressure. I don't know, chemistry. When I put my hands up and I say I don't know, I tell you what, we don't know. People have looked at this problem for 70 years. And they think both that there's a core and there's not a core. The thing that we know for sure is that at the very beginning, we think, sorry, I should say this differently. The thing that we know for sure is that we don't know whether or not it currently has a core. We think with a high level of confidence that it needed to have had a core. But other people argue with that as well. We just didn't, there's no photos of the time. We can't go down, we can't look, right?
So is that like the same with the other, like gas giant too? Like does yours?
Yeah, it's a very good question.
Oh,
Or any of the gas?
yeah,
Yeah, it's a good question.
great. You know, when you figure it out.
Well, we don't get all of the answers in science. We have what we have, and we don't have what we don't have. You want me to just lie to you? There's Hello Kitties at the bottom. Okay. So should Jupiter have a magnetic field? A, no, the core is solid from all that pressure. B, no, it's not rotating fast enough. C, no, the interior is too cold for convection. D, yes, a moderate magnetic field since it has a core that's 10 times the Earth's mass. E, yes, a strong magnetic field due to metallic hydrogen.
extent?
Don't ask yet, just think about it for a second, just test your own knowledge.
I don't know.
My God. My God, you know what I'm saying? Ready to vote? Vote on 3, 2, 1. Okay, alright. Anyone wanna argue for their point?
Well, you were talking about how metallic hydrogen acts like a metal, which means it conducts electricity, and Jupiter has the fast rotation. Let's say there is.
So you say there's magnetic field, so one of these two.
I'd say B.
You say E, you think it's strong. You don't think it's weak. Who likes Jupiter's magnetic field bigger than Earth's? Who likes Earth's magnetic field bigger than Jupiter's? Who likes, I hate trick questions. Alright. So this is Jupiter. Jupiter, if you could see in the radio, is the biggest object in the sky. So this is the Earth to scale here, and this is the Earth's magnetosphere. Just a baby magnetosphere. Just a baby. And that fits right in here. Okay. So this is a massive magnetosphere, of which we have a spacecraft, Juno, which is flying through it. So the reason why Juno has such a strange orbit is that it tries to sample a lot of the different places in the magnetosphere to understand the magnetic environment in which Jupiter and the rest of the satellites live. And so what you can see here, this is fully zoomed in, that you have this structure. There's Io. Io makes a torus. It's basically another word for a donut. And it's a donut full of atoms. And those atoms get trapped. They go along magnetic field lines and then they smash into Jupiter. Jupiter has a big magnetic field and it creates aurora. So we said when we saw Jupiter in the first place, we saw this footprint called the Io footprint. It's material that gets released from Io, travels along magnetic field lines and smashes into the top or bottom of Jupiter. Okay. Big. Massive. This is so big that humans living in Jupiter's magnetosphere would have a really bad time. So we talk about magnetospheres as being necessary to protect us from the sun's solar energetic rays. It just so happens if it's too big, it becomes problematic as well. So I don't know what you want, I don't know what you want to do with that information. Here's all of the Jovian planets. They have substantial magnetospheres. That's the size of the sun to scale. Of course, we have not talked about the sun's magnetosphere. It's very big. But the size of the sun here, right? Next time you look out in the sky, like 6 suns big. So if you look up at the sun, don't do it. But if you look up at the sun, it's probably about the width of your thumb, held at arm's length. So if you want to see how big Jupiter would look on the sky, if you could see the magnetic field, about 6 times as large. So it's about that big. Right? Look out on the sky. Wow, that's monster. Right? 6 times larger, 7 times larger than the moon. Yeah. Pretty cool, right? And then you have Saturn. Saturn's actually kind of annoying, right? Because it looks really beautiful. It has rings on it. But if you get rid of the rings, it's kind of just like small for it. Who cares? Uranus is better. You'll also notice the orientation here. So here's the rotational axis in white, and there's a dipole or tilts to it. Just like on the Earth, the rotational axis and the north-south do not overlap. North pole has been moving. The magnetic North Pole has moved over the past 40 years. Pretty cool. Headed towards Russia right now. Get to have it for a little while, and then it'll come back, then it'll go over there. It's cool. They have some fun fluid dynamic simulations that show have what's called a reversal of the magnetic field. North becomes south, south becomes north. And the sharks get really upset about this. Sharks use magnetic field of the earth in order to navigate where to have babies and where to go eat foods. Have something inside of their skin called ampullae lorenzini, which follow magnetic field lines. They're
Like a little.
it's like built into their skin. It's like there's this, if you look on the edge of a shark, you'll see like a white line or a black line. Those are the ampullae of lorenzini.
So like disorient states, where.
They can just sense the magnetic field while they swim.
Then you feel it like shift.
Yep. I'm reading a book right now, which is fantastic, which is about Umwelten, which I talked about before, which is like how everyone experiences the world. And animals that don't have eyes, for example, have less sophisticated eyes and think, well, that must suck for them, they don't experience the world. The reality is there's a vast array of ways to experience the world, right? And it just so happens that sharks can feel electric fields. It's something that you can't even conceptualize possible.
I think humans have anything cool like that.
Why can't humans have anything cool like that? We have very complex eyes. You want to know a fun fact about your feeling? Okay, so you have your fingers like this. You run them across some object. Okay, you can feel the difference between raised ridges that are 10 nanometers apart. For an idea of what that is feeling individual molecules. What? He is not happy with this as an idea, but this has been shown time and time again. We're not the best feelers in the world. We're not the best smellers in the world. We're not the best seers in the world. We're not the best hearers in the world, but we are very well adapted to our environments. There's a reason why we've dominated the whole world.
We're average, and that's what we're good at.
We're not average. We're above average in a lot of respects. But depending on how you construct it, right? We're actually quite good at smelling things. So you can like smell in a line, like sniff stuff. You can find out where stuff has been. You'd be surprised at how quickly you can teach it. We can't see in the infrared. That sucks. Can't see in the ultraviolet. That sucks. But we just built some stuff, and now we can. We can see in radio. No other animals can see in radio. Not me. Okay, any other questions?
That drops off here.
I'm gonna end it early because we could go into like rings and moonlets and stuff, but right? I just wanna go home. Don't wanna tired.
You want early spring break.
I didn't want an early spring break. I don't know if I can clean my office. So I'll answer any questions about Umwelten. And other than that, have a nice spring break. There will be no homework this year or this year. This spring break. And we'll do a new homework that I'll release on Monday when you guys come back.
So then you should put all this one.
No.